Alright, so finally we're in the last part of question 1, and this time we're doing something almost exactly like what the professor covered in one of his lectures on the YouTube video. So now we have a bunch of we want to send a bunch of messages across, or symbols across, right? We want to send 1,000 symbols across, but we know that 0.8% of the time, or rather 80% of the time, our packets get dropped. So we want to send enough so that with 99% probability that at least 1,000 will get across, right? So how do we go about solving this problem? Now we have, let's say k is equal to 1,000. So we want 1,000 packets to get across, and let xi be the indicator rv for the ith packet. Basically it's 1 if your ith packet gets across, and it's 0 otherwise, right? So expectation, it's a Bernoulli random variable, so expectation of xi is just going to be 1 minus p, because you want it goes through with probability 1 minus p. So p is equal to 0.8, right? Probability of failure is going to be 0.8, and expectation of xi is going to be 1 minus p, right? So now we send n packets, and we hope that we have greater than n packets, we have greater than k packets, which actually go through. So let's have a random variable t, which represents the number of packets which goes through, right? So, or rather, number of unerased packets which go through our network. So we know that t is equal to sigma xi whoops, erase that. I is equal to 1 to n, right? Because xi is the indicator random variable that the ith packet goes through. So the sum of all the indicators is equal to the total number of packets that go through. Now what do we want to bound? Let's work on this side of the screen, and we'll come back to that one. So we want to make sure the probability that t less than k is less than equal to, that is, that we are able to send across less than k packets. We want the probability of that to be less than equal to 0.01. Now let's try to mold this again into a form which we know how to deal with in terms of Chebyshev's inequality. So probability of t less than k is equal to probability of negative t greater than negative k, which is less than equal to probability of no, I'm not going to say less than equal to, I'm going to do it one step at a time and say it's equal to probability of expectation of t. So I'm just adding expectation of t to both sides, expectation of t minus k, which is less than equal to probability of expectation of t minus t is greater than equal to expectation of t minus k. So the event being like the probability of the event we're finding below is going to be greater than the probability of the event we're finding above, because the event above is a subset of the event below. Now if we add the other term to introduce the absolute value sign, that is, we add the event which states that probability of t minus expectation of t greater than equal to expectation of t minus k, then we know that whatever we're going to add is going to be non-negative. So we're just adding this to account for both sides, for this inequality to hold from both sides. This is just like question 5. So now this isn't exactly a form which we're used to in terms of Chebyshev's inequality. So therefore we have probability of t less than k is less than equal to probability of absolute value of, I'm not going to say expectation of t here, I'm going to say t because people are more used to that, t minus expectation of t, even though it doesn't make a difference because of the absolute value sign. It's greater than equal to expectation of t minus k. This is less than equal to variance of t divided by expectation of t minus k the whole square, and this we want less than equal to 0.01. Alright, so now let's go back here and calculate what exactly expectation of t is. What is expectation of t? If you have each and every xi has expectation 1 minus p, then t has expectation n times 1 minus p, right? And if, okay, and 1 minus p is equal to 0.02, so this is just 0.2n. What is variance of t? Variance of t, because this is just a binomial distribution, it's n times p times 1 minus p, which is equal to 0.16n. If you just calculate p times 1 minus p, you get 0.16. Now let's go back here and substitute these values in. So we have variance of t divided by expectation of t minus k the whole squared is equal to 0.16n divided by 0.2n minus 1000 the whole squared less than equal to 0.01, right? This, when we solve for this, as in when we rearrange this, we get a quadratic, and I'm just going to write the quadratic here, n squared, because I'm sure everybody can do this on their own. Negative 416 plus 1 million is greater than 0. So yeah, we see that the numbers here are of very, very different orders, but that's only because n is going to be a fairly large number in order to force k, in order to force the number of packets to be greater than equal to k. This gives us two numbers, gives us n greater than equal to 6, as in when you solve this, plugging into something like Wolfram Alpha or whatever, it's going to give us n greater than equal to 6629, or n less than equal to 3774. Obviously this is not going to hold, because this is telling you that if you send anything less than 3774 packets, you have over 99% chance of k is equal to 1000. Actually it's not, it's actually telling you the other thing. It's actually Chebyshev inequality has an absolute value sign, and it's bounding the other side. So it's telling you the opposite of what you need. And now, so what we really need to consider here is n greater than equal to 6629. So you won't be really expected to solve complex quadratic equations. You are expected to know exactly how to use the quadratic equation formula, as in negative b plus or minus root of b squared minus 4ac divided by 2a, that formula. And you are also required to be able to explain exactly which one of the roots are relevant and which one is not, and why the other one is not relevant. But you are not expected to come up with these numbers on the exam. Alright, so n greater than equal to 6629 is the final value which we're going to get for the number of packets which we need to send across, so that at least with at least 99% probability 1000 will get across. Alright, so that's it for question 1 of homework 13.